There you go. Alright guys, welcome to the... Oh yeah. Welcome to the continuation of the CNN workshop from last week, and we're also going to go into transfer learning this workshop. So once again, we're just going to cover just a very simple CNN, how you guys put that together. We're going to just review that, and this should be kind of a review and showing you guys some more of applied stuff. It would be great if you guys can code along, just so you get the muscle memory at least and remember what the frameworks are. So I'm just going to start off by importing a few things.
If anyone needs help like getting to like collab their Google account,
Yeah.
it should be like collab.google.com.
Yeah, like if you just open up, just type in Google Colab, it will be top link, you know, just go here. So once again, Colab just has all these packages and makes things nice and pretty. It's just a Jupyter notebook. Yeah, and GPUs. So the very first thing when I make this notebook that I'm going to do is I'm going to change my runtime type over to GPU. This will just allow me to, once again, mount data onto the GPUs. If you guys know anything about GPUs, that just makes things exponentially faster because they can do a lot of parallelized executions. So I'm just going to import a few more things. Import torch.optim as optim. You guys will see what these libraries do later on. So just as a show of hands, who here has touched NumPy and or Matplotlib? Alright. Who here has no idea what those are? Okay. So NumPy is numerical Python. It's basically a library that allows you to do a lot of operations kind of vectorized. So it's a really nice package. If you do anything data science, you're going to become very intimate. You're going to become very familiar with it. So yeah, it's like a very standard Torch Vision Python package. So we'll be using NumPy, Torch, and Matplotlib. Matplotlib we're going to use to just show stuff.
Did you make the text edit?
Yeah, no problem. Alright, cool. Alright, so the first thing I'm going to do is I'm going to just download the data. So Torch Vision.datasets gives us this is a nice function that just allows you to download whichever dataset you want. So we're going to use MNIST. If you guys remember what that is, that's just going to be digits. So to download it, we're just going to say, okay, we have some variable called train. Train equals datasets.MNIST, because MNIST is the dataset that we're going to use. We're going to set the root directory, so that's where it's going to locally download the data to. We're going to tell it, all right, we want to download. Transforms, Devin's going to go into later, and train is true, because this is going to be our train data. We can also do the same thing with test. For test, it will be the exact same thing as this line you see here, except you will just be turning train to false. If you run this, it's going to take a second. So this runs in Google Colab. You can see like local files are at by just clicking on this arrow on the left side, clicking on files. That'll show you some stuff. So as you guys might see, we have data here. That's going to make the MNIST folder, and you can have process raw stuff, yada yada yada. So that's just where the data is going to be held. All right, so this datasets object gives us various functionality. So just to see like the various methods that we can call or like variables inside of this, you can in Python you can just do dir and type the variable name. This is going to output just a list of things you can call from this. So the two things I'm going to grab is train data and train labels. So I'm just going to say, all right, train of x, train data, train y equals train labels. See dataset looks like. So the structure of, without looking at these two lines, when you do datasets.MNIST, it's going to give you an array of tuples pretty much. So if I do the length of train of x, you'll notice this is going to print out 60,000 because we have 60,000 data like images that we're going to be that's inside of this data set. Similarly, if I do that of just the first index, it's going to print out, oh, this is of x. This is going to print out the length of tuple. It's going to be 2. So if I just do train of 0 of 0, you'll notice this will give me an image. So the type of this is just going to be a pill image. Don't have to worry about what that is. You can just think of it as an object that is an image inside of Python. So notice how train of 0 of 0 gives you the digit 5. And if I want to get the classification, because that is our input, so classification of this will be held in the 1th index, and that'll give us 5. So all train of x is going to be is it's going to be that image except as a numpy array, I believe. So if I do train of x of 0, you'll just get a bunch of numbers. So these are just the RGB values of this image. And train of y similarly, not what I meant to do. This is just going to be the classification. So you'll see it's a tensor saying 5. Everyone good thus far? So yeah, we have the data loaded in memory, and we can do some stuff with this. So the goal of this CNN is we just want to make a classifier. So we give it some image, let's say digit 4. We want it to output 4, just so we can, figure out what it is that we're looking at. So to start with this network, just as a show of hands, who remembers like kernel size? This is like strides, paddings, stuff from the last workshop. Are we like iffy on that? Okay, so just to recap, convolutional networks, how they work is we have a thing called a feature. Think of it as a sliding window. It's going to have some size, and we're going to slide it across an image, and it's just going to do dot products and extract features from that. So the filter itself is going to have its own weights, yada yada. So in PyTorch, we can make our own model or network. So you can do this by just making a class. It's going to inherit from nn.module. So this is defining, so this module thing we imported up here. Should have this line. This will allow you to do forward propagation and set the parameters of this network. So there's only 2 things you need. First thing is you need to call super, pass in the name of this class, self dot init, and then whatever your parameters are. So let's say we want this to be very simple. So we're just going to have one convolutional network, self.conv equals nn.conv2d. So conv2d is going to take in a couple parameters, so I can show you guys. Once again, Python is nice. It has lots of different functions that will show you what a function takes and whatnot. So if I do help of conv2d, I go all the way up. We should see the various arguments that takes. So it's going to take in input channels, output channels, kernel size, stride, etc., etc. So input channel is just going to be think of it as the number of values inside of so our image is currently in grayscale. So if I print out this dot shape, actually let me insert train of x dot shape. We'll notice that RGB images, usually there's RGB values. So this would be a 20 by 20 by 3. The MNIST dataset, if you guys remembered, the image was black and white. That's called grayscale, so there's only one number. So because of that, there's only going to be one channel. So we're actually going to want to reshape this just to fit the structure of conv2d. So we're going to do reshape this into a -1. That just means any size, or any number of batches. 1, because grayscale, so there's going to be one number, 28 by 28. Alright, and now if I print out the shape of this, 60,000 batch size 1, number of channels, grayscale 1 number, and it's a 20 by 28 image. So the number of channels we're going to take in is 1, because it's grayscale, there's 1. Otherwise, if it was RGB, it would be 3. The output channels, so output channels are just going to mean the number of filters we actually use. So we're going to say 9. Remember, each filter that we add creates a new activation map, adds depth onto the next input layer. Kernel size, we're going to set to 3, so it's going to be a 3 by 3 sliding window. Stride, we're setting to 1, padding 1. So with this strident padding, all that means is in the next layer, our image isn't going to shrink. It's going to be the same dimensions of 20 by 28. And the second layer we're going to add, very simple, self.dense. So we're going to make a linear layer or a fully connected layer. And it's going to take in 9 activation maps. And they're going to be of size 20 by 28. We're going to output 10 classifications for the 10 digits in our data set. The next function, I completely forgot to put this inside of a init. My fault. So yeah, this is supposed to go inside of an init function. That's your constructor. And yeah, my fault. The next function we're going to add is forward. So forward, as you might imagine, just means forward propagation. So that's just going to pass our inputs through the network and get values out. So for forward, we're going to say, okay, we have A1 equals self dot f dot relu of self dot. So what this line means is we're going to take our input x, which is going to be like some image, for example. We're going to pass it into our convolutional layer. And then we're going to apply relu onto this. So f, I forgot to import torch.nn.functional. It basically allows you to apply functions onto tensors. So f.relu, yep, sorry. Stop me at any point, I'll go back. I don't know if I'm blazing through or, going slow. Yeah.
Is it required to reshape the x values that we did?
So yeah, the reason why is conv2D expects a 4-dimensional tensor. So if I go into the PyTorch documentation, so the reason why I shaped it before, if you remember, it was 60,000 by 20 by 28. That's a 3-dimensional thing. So the 2D is expecting this digit to be the number of channels. This is the batch size. And this is the height and width of the actual image. And if you're ever confused on stuff, you can just always go to the side, just look up, all right, conv2D right here, and you'll see it right here. Batch size, number of channels, height, width. So yeah, so that's like my little bit of processing for this. Any other questions thus far? Everyone good? Okay, so we have our A1. So we're going to apply the activation function onto this layer. We're going to say our output is just going to be, before we even do that, what we want to do is we want to flatten this value because we want to pass into a dense connected layer. So what I'm going to do is I'm going to say flatten equals A1 dot shape -1. We have 9 activation maps, each of which should be size 20 by 28. That's going to flatten it such that we can just pass that into our dense layer. So f.softmax, self.dense, we're just going to pass and flatten. Yeah, this is going to give us numerical vector of 10 numbers. So return output. And yep. So just to see like what an output would be at this point, I can say, all right, let me first make an object, and then we can do either dot forward or we can actually also just pass it like this, just give it some data. So I'm going to just say, all right, train x of 0, and the reason why I'm going to add a slice right here is that just preserves, it makes it into a 4-dimensional, because if I just do this print train of 0 dot shape, this is a tuple because that's not x. This is going to be a 1 by 20 by 28, but remember we're expecting a 4-dimensional vector for convolutional, for conv. So I'm instead going to do this. Take slice, and it's going to be a 4-dimensional vector, which is what this is expecting. So if you just pass this through, I have to turn this into a type. Torch.float tensor. Dot float? Alright. Dot float. Okay. method. Dot long. All right. CPU. All right. So as you guys can see, we got a vector with 10 different numbers. So dot float, dot long. This is just kind of just like it wants a specific data type, which I forgot to convert it previously. So these are just like little bugs that you guys will be able to patch, with experience. So right now, it doesn't really give us a good classification. So what is this net of? What is this actual image that we're looking at? We can print out train y 0, and it's supposed to be 5. So the label for this image is 5. If I do np.argmax, all that np.argmax does is it's going to give you the index of the largest value. So if I did like something like this, it'll print out 1 because it's the index of the largest value inside of this array. Yep. Train test? Yeah. Right here or above? Okay, yeah. No, so this is a tuple. So it's going to be an array of tuples. So train underscore, yeah, I had mistakenly, I was about to do type, but I erased that because it was supposed to be the train underscore x. So this is our actual data. So this is just going to be all of the 0 elements inside of all the tuples from train, if that makes sense. Any other questions? All right, so yeah, np.argmax is going to give you the index of the largest number. So, okay, if I do np.argmax of, let's just say this was our output, equals that. So we know the actual label is going to be this. So what does this give us? I have to turn it to a numpy because it's currently a tensor. So remember in PyTorch, you're able, okay, I have to detach it first. And then it's plugged into my CPU. Oh no. All right, so detach just removes it off of the GPU onto CPU, then .numpy converts it to tensor. Just, it's a little monotonous, but that's just how we get it into a different library. So this happened to get the right classification, which is kind of ironic. But let's try a different image. Let's say, I don't know, 5:6, right? This would be 5. All right, what does it print now? Yeah, so the actual label was 2, and this guessed 9, which as we can see is not it at all. So we want to train this network such that it is able to guess what the actual image is going to be. So that's just going to bring us into the training cycle. So to train, we're going to define an optimizer. So in this case, we're going to use atom optimization. You guys might not remember too much of the specifics from the last workshop, but basically it uses RMS prop and weighted gradients in momentum. And it's a very kind of standard optimization method that we use. And we're also going to use cross-entropy loss function. So the difference between squared mean error and cross-entropy loss is better for classification, while squared mean error is better for regression. And that's just down to the derivation, which we didn't show you guys, but you guys can look that up if you're interested. So cross-entropy is the best for classification, which is what we're trying to do. So I'm saying, okay, optimizer equals nn.atom. Going to take in net, so our model parameters. This is how it knows, okay, what stuff are we actually updating. And remember, our model is inheriting from nn.module. I'm going to set the learning rate, 0.01. And we're also going to set our cost function. So I'm just going to call it costf equals nn.cross. This is supposed to be optim, my fault. Optim cross entropy loss. And yeah, I'm also just going to make an empty list just because I want to record the loss as we start training. So now I'm going to say for I in range of, let's just do 2 training iterations. So we're going to visit every single training element twice. So the very first thing I'm going to do, optimizer.zero gradient. This just clears the gradient and resets us so we can redo the optimize whole training step. I'm going to calculate the actual loss, so I'm going to say okay. Well, before we can calculate loss, we have to make a guess. So outputs equals our network. We're going to pass our entire training object into it, train_x. After I pass in our that there, we're going to get the loss. So loss equals cost function. We're going to pass in the outputs and train y. So outputs should be in the same shape as train_y because that's just labels. It's just going to pass this into the cross-country loss function to get your number, saying how bad did you do. After that, I'm going to say, okay, loss.backward. That just calculates the gradients, which we need to do gradient descent or Adams optimization. Following loss backwards, I'm just going to append it onto this list so I can look at it later, plot it. And finally, I'm going to say, okay, we're going to actually train. So optimizer.step is going to actually update all of these things. So if I run this, hopefully it doesn't yell at me as that's running. Currently, I don't think I have anything mounted on GPU, but we're going to do that later when I increase the actual number of training iterations. So to plot the actual loss, we're just going to do plot. So once again, plot we imported up here, matplotlib.pyplot as plot. So just going to do this of losses, plot.show, plot.close. So show plot just sends the data into the plotting thing. Show actually presented, and close closes the file descriptor. So notice we only put 2 points, so of course this is going to be kind of linear. So let's say, all right, instead of 2, let's make 5. And before I even do that, I'm also going to mount everything onto CUDAs just so it's faster. So make sure your run type, if you go to change runtime type, is GPU. Otherwise, the step's not going to work for you guys. So I'm going to say, all right, I'm just going to make this a CUDA object. Same with here. So you can just do .CUDA on the train_x and train_y. Going to initialize the network and put that onto CUDAs. And after I do that, I'm actually going to bump this up to 10. I'm just going to run everything over from this top because it has to rerun the CUDA stuff. Any questions thus far?
So that is the optimizer, like it's not necessarily like the step, is that separate from calculating the loss? Two different things going on?
Yeah, so calculating the loss, you can think of it as just, okay, if this was squared mean error, it would just be, we have our guess outputs, so that minus the label squared, pretty much.
So the optimizer doesn't do that.
So we have this dot backward. This is going to give you the gradients, and the gradients is what the PyTorch is very magical, and I'm just like, would you like to go into more detail?
Basically, you calculate the loss and then you compute the gradients. So then, once you have this gradient, you have the gradient term that's stored as like a vector, and then you have your parameters. So it's gonna, the optimizer step is supposed to take the gradients and then add them to the parameters so that they update, right? And that's the optimizer dot step. But in the case that you don't do zero grad, you could just keep accumulating this gradient, and then at some point when you call optimizer that dot step, it would take that and then add it to the parameters.
So it's all shared together.
Yeah, it's all under the hood, so very magical.
That's good.
So as you can see, we added 10 steps, and this is looking more like a loss function. So we can see our loss is decreasing over time. So you can imagine if we did more, it's going to be even flatter as time goes on. So the reason why we use activation functions is because we might have nonlinear data. So imagine instead of adding value, I just completely remove this. Let's just see what this would look like. I'm going to add the softmax just because. Should I take it out if I'm showing winners? Yeah, I'll leave it in. All right. So let's see how this looks after 10 training versions. Huh. Try without? Yeah.
It's just like you want to output probability, so
Yeah, so this is a way more wonky. So yeah, that's why we add activation functions, kind of.
you can just like type that outputs and the floater. So you don't have
So yeah, these are like,
some of the weights are shown.
yeah.
The outputs.
So it's
But if you put it in
output.
softmax, it'll be between the
Yeah. Okay, is the code working on everyone's machines? Does anyone have any questions about various functions here? If not, we're going to move into transfer learning. Okay.
Let me see. Yeah, so the actual graph might be a little different, but the general concept is if this is like a decreasing thing over time, it's fine. So even like in the one graph here, this decreasing.
But like, I'd imagine it wouldn't fit too amazingly if I gave it like actual test data. And the other nonlinear when I had value, it just looked better. It's more coded. So yeah, as long as in general it is a decreasing graph, like you'll be fine. Yeah. All right. Does anyone have any questions about the functions shown? Want to try out having more complex stuff, or are we good henceforth? Going once. Let me show fingers. 1 through 5. How good is everyone? 5. Questions. What are you unsure about?
The things that I'm not sure about
Okay. When we go for the next one, a good amount might be redundant. So like, if you like see a moment where you're not sure what's happening, ask a question.
Okay. All right. I guess we'll move on. So yeah, take it away. All right. So just a little. Okay. Good. So this is just our 4 slides for today. So a brief sneak peek at the code we're gonna be doing. So a lot of this is pretty similar to what Curtis just did. Like the general like idea of like this train that we made, things like that. And then we'll go in, see how like you test the accuracy, elaborate a little more on how you can handle PyTorch, handle data in PyTorch. So that was just a sneak peek at the code. But so the difference between what Curtis did and what I will do is that we're going to be doing something called like transfer learning. So what transfer learning is doing is it's taking knowledge that was learned on like some data set and applying it to another data set. So take this diagram, for example. So you start on this like source pass / domain. Like this is just where you're starting at. Like imagine that's a data set. Let's say if it's like handwritten digit data set. That's what you're training this model on. And we go through this training procedure, and then all those weights are adjusted. You end up with these kernels, these filters that are say something or reflect something that's in the data. So that's all stored in this network now. That's information that's valuable that you just learned. So that's the knowledge that you now have and that's encoded in this network in your model. Now, let's say we started with this handwritten digit data set, and now we want to start looking at something like fonts, maybe. Well, that's not the same thing as handwritten data sets, but it is very similar. So can we take what we learned about handwritten digits and apply it to like fonts or something? So we take the knowledge and then we do this thing called like fine-tuning, transfer learning, such that we're able to apply it to like a new data set. So we're taking something, you learn something about it, apply what you learned onto something new. So what this actually practically looks like is, imagine this is your whole neural network in the beginning, and this neural network is trained to like say, okay, if this is like a handwritten digit, which one it is,
So what we literally do is you chop off the end of that network. You say, okay, we don't need to output between 0 and 10. Let's say it's a different size output. For a different task, we just make it such that those weights will lead to an output such that it's going to fit our problem. So we'll actually see an example of this when we go through it. But what we're doing is we're chopping out like the end part, and we're keeping the weights that we just learned. So we're literally taking the weights we just learned on one data set, and we're going to apply it to a new data set. We just need to make sure our network is going to be able to output the right thing that we want. Does that make sense, kind of conceptually, what we're trying to do here? Sweet. So, very first. Okay, I'm trying to think the best way to go through this. So, I'm just going to copy and paste this here. A good amount is what we just did from before. So you have Torch, just overall PyTorch package. We have an optimizer. We're going to use that like gradient descent or Atom. The neural network, that's our like PyTorch's neural network module, our sub package that will allow us to do handy things specifically for creating neural networks. Then functional. So again, we saw f.relu. So it's going to allow us to apply things like activation functions onto our layers. And then Torch Vision, so that's a package made for Torch, PyTorch, specifically for computer vision type stuff. So CNNs, which are very common to use, computer vision, they will have pre-trained models if you import this one sub package, which is what we'll use. We won't have to go through and train our entire thing and then transfer that to a new thing. We can just use a pre-trained model as it is and then adapt that to our need. So we're also importing this thing called transforms, and that's going to come into how we handle our data. So let's run this. And so what I'm saying here on this torch.cuda.isAvailable, CUDA basically is reflecting the GPU there. It's the, I guess, software that runs on GPUs. I believe it's a programming language. But right now it's saying false, that we don't, this is basically saying, is there a GPU? Right now there is no GPU. So if we go do what we did in the last workshop, change this to GPU, and then if we rerun this, we should get true. Okay, so we have all these packages. I don't think we'll need to import anything else. There might be one or two things, but we'll come to that. So the very first thing that you always start with when you think about machine learning is the data. So let's go ahead and get our train loader set up. Who does this? Am I importing that? Oh. Okay, it's coming from Torch Vision. That's where it is. All right, so Torch Vision.datasets dot cipher 10. Torch Vision is slightly different. So again, we're going to still take where we're downloading, train, download, transform. I'm going to take this, and I lied, this is not the loader, but it is the set. So again, it's going to download into a data directory. This is our train set, so we're going to save some data later so we can test it. And then we're going to download it, and we're going to transform it. So let's talk about this transformation here. So we had this data coming in, and as we saw in Curtis's workshop, remember that like PIL image, like whatever, which is basically just how Python handles taking in image data. It's almost like reflective of like a file in your system. And so when we do machine learning, we're not working with like that type of object. We're working with like matrices, zeros, ones that indicate like, okay, what are those pixel values? So that's what this 2-tensor transformation is doing here. We want to transform that into something that we can actually work with in PyTorch to have that tensor. And then this normalization here, this is kind of unnecessary for this part, but what it's doing is, if you remember like a z-score from your statistics course, this is the mean, and then this is the standard deviation that you're enforcing, such that everything's going to be centered around 0.5 with a standard deviation of 0.5. So that's going to be every pixel value that's in this image that's going to go through these transformations. So that's just going to help normalize the data so that the model is able to learn better. That's because gradient descent likes the data when it's all nice and centered. So the final thing is this resize transformation, which I'm going to want to talk about in a little bit here. But for now, let's go copy paste this. That's going to be our test set. And we just change this again to false. We still want to apply the transformation to it because this is again just image data as well. Now for our data loader, this is going to come out of torch.utils. So we didn't see data loaders before in the last workshop, in the Curtis's. Curtis was loading it in, handling himself. And so data loaders are useful when you want to do things like enforce a batch size, shuffle your data for you, so make it random so your network doesn't memorize like an order of the data you're feeding in. So also PyTorch, since things like number of workers, it's doing some like threading underneath the hood for you so that things go faster. But it's taken in the training set, and it's basically doing all these nice things that are really useful for us when we do machine learning. So before this, we should add a batch size. Let's just make this 4 for now. We can come and adjust that. After this, I recommend you take this code, play around with these different hyperparameters that will declare up here, and see how that's going to like affect the performance at the end. We also need a data loader for our test set. Let's just call this our test loader. It's going to take a batch size, same number of workers. Just we don't want to shuffle it at the end, just so we can like keep track of that if we want to test it at a certain interval. Data train false transform. Okay, that should be test set. Gotta call me on these things, guys. Okay, let's run this. So this is again just going to download. It's all stored. Torch Vision makes it really easy to download data sets about this. Let's actually talk about the Cypher 10 dataset. So what exactly is it? That might be a better one. But right here, the 10 is for 10 number of like outputs. So before we had like 10 handwritten digits. Now we have 10 different classes, being airplane, automobile, etc. And then these are the type of images you see. They're pretty small, so this is kind of like, again, like a toy data set, but still a good amount more complex than something like just some handwritten digits. So this is the type of data that you're dealing with. It's always a good idea to take a look, play through your data set, get an idea of what you're going to be actually modeling. So yeah, batch size not defined. We got to run this first. Okay. So I had a part in here where we went ahead and like played around, like pulling in the images itself. For the sake of time, let's not do that, but I'll put a link to this master document if you want to go ahead and do that. So now we're going to go ahead and get this pre-trained model. So if we call this ResNet. Yes. Yeah. So let's go with the 18. Then we have this pre-trained. This is true. So what this line is doing is Torch Vision, which is where we imported this models object from, contains a lot of like architectures that are already there for us. So ResNet 18, we'll actually be going into this in depth the next week. ResNet is a specific type of CNN. It did really well on like the famous like ImageNet data set. It's a really nice idea in how they like made this advancement. So again, we'll be going over that more in depth next week. We'll like take the research paper, we'll break it down, and then we'll actually kind of code it up. So stay tuned for that. But for the sake of this right now, this is just some convolutional neural network that we're downloading from this Torch Vision package, and it's pre-trained. So it was trained on ImageNet, this really big, massive data set. Let's do it. And which literally has like 1,000, literally has 1,000 classes, where before we had, right now we're just doing 10. So it's a bunch of just images all over the place. I believe they were scraped from like Google Images, and then labeled using like Amazon Mechanical Turk. So it's a really famous data set. It's really big. It's kind of, you'll see people say, oh, like, but how did this model do on ImageNet? So a data set to be aware of. So this is going to come down. It's going to be pre-trained. But we're going to wrap this in our own class. So if we declare a class, call this our pre-trained model. And then this is also going to take in neural network.module, which is just going to allow us to do extra things. It's the PyTorch way to extend a neural network module, which is to create your own neural network. So let's do that initialization class. This contains self. Then we have to do super. We're going to have to call this. So this is calling that like neural network.module. And we're passing in this and I believe self without the nit.
No, you do super.c dot.
So without this, they got rid of that? That's beautiful. Ignore that. Beautiful. Okay. Yeah, so now what we're going to call here is we're just going to say ResNet is this ResNet that we just came in. Actually call this pre-ResNet so that doesn't get confused ever. So what this is doing is just saying within our neural network we're going to have this pre-trained model already. But remember how we talked about in the slides over here that we want to preserve, that we want to just use what it was already learned and just update the end, just like fine-tune kind of how these features, how these like filters that it learned are going to be used to make an actual prediction. So what we do is we're going to go through self.resonet's parameters. I need to write it for it. Now, these are parameters, so what PyTorch is doing under the hood is it's keeping track of this like computational graph that it's forming and keeping track of that like derivative, that gradient, so that you're going to be able to backprop at the end of this and actually update it. But we don't want this to update. If we're saying, okay, it has things that we already need to learn, we don't want to spend all the time, spend all those extra resources computing those gradients and then making those updates. So we want to tell PyTorch, okay, stop looking at these gradients, stop taking these derivatives. So what we do is there's a property of parameters in PyTorch called requires_grad. And normally this would be set to true if you're training this and you're going to make these updates. But right now we don't care about that. We just want to say it as is. It's pre-trained. It should know something, and we just want to exploit that at the end. So we're just going to say p.requiredgrad, and we're going to set that equal to false. Now I'm going to go up here to, before we move on, to demonstrate. Let's print what this network actually looks like. So you see this is like a pretty, like this looks pretty complicated. There's a lot of things going on, but you still see that we're using ReLU. It's using convolutional neural network, something called batch norm, which I think we might mention next week then. Still using a convolutional layer, and it's just a ton of these stacked on top of each other all the way down. And then finally we have this linear layer, which looks similar to that like dense layer at the end of these neural networks that are just used to take these filters, what those learn, extract it out, and make some like classification based on. So this is called FC, which stands for like fully connected. Like convolutional layers, they're not fully connected. It's just like a filter sliding over. But this is fully connected with this linear. And you see this out feature is 1,000, and that's because, again, we go back to ImageNet, and there were 1,000 different classes. I think I actually have a list of all these classes right here. Yeah, like these are all the classes PyTorch knows, or I mean Torch Vision, this pre-trained model knows. Like there are all these images, 1,000 different ones. So we're using Cypher 10. We only have 10 outputs, not 1,000. So we need to change this, and we want to update that last part so that we'll be able to use what was learned in all these big block layers up here. So what we do is we go self.resnet.fc, and we're going to set this to our own linear module. And we're going to take in its in features. It is still going to take in 512 because that's what's coming out of this last in like the convolutional part of ResNet. And then we're going to output just 10. And we also want to make sure that we index properly. And we're going to set .requires grad to true. Just being explicit here that we are now calculating the gradient so that we will update just this part. The rest of this network is going to stay as the same. It knows something about like the data that's in ImageNet, which should be applicable to Cypher 10. And we know that because these images generally seem to be similar to these images. So there is probably something useful in what was learned by that data, by this network on that data set. So if we go ahead and do that, we need one more function here, and this is the forward. And this is going to take itself, and it's going to take in the input here. And what we literally just need to do is return self.resnet, and then pass in x. So that should be all good. And here, so we're passing an x here, which is an image from all these data sets, from all these like data things that we defined up here. Which brings me to this resize transformation. So the images in Cypher 10 are smaller than the images that are used to train ImageNet. So we need to just resize these images such that it's going to still fit into that like input going into ResNet that was designed for ImageNet. So that's this resize here. So that's why we have that. So we basically adapted a model that was trained on a totally different data set with different inputs and different outputs to our new problem with some inputs and different outputs so that we're able to use it. And this, what we'll end up seeing is that this is going to like train faster. It's going to already know, okay, kind of where to look in an image. Yeah, so let's go ahead and do this. Maybe we can error. So let's declare a model before we train this. This is going to be pre-trained model, and then it's just that. And then we also should have a loss function or cost function beforehand. And we're going to do cross entropy. Is there a loss? Yes. Okay. And then our optimizer is going to be equal to optin. Did we input that? Yes. Yeah. So this is going to be optin.atom, and then we're going to pass in our model.parameters, and then our learning rate is going to equal. So let's define this back up here with all our head parameters. And then this is going to equal 0.001. That's generally just like a standard learning rate to play around with in the beginning. Okay, so these are the three things that we need. We need a model, we need a loss function to tell us how good or how bad that model is doing, and we need an optimizer to actually update the model such that it's going to be better the next time around. I spelled something. Where is this? What's the name? Pre-trained model object. Okay, so we're going to have another hyperparameter, and this is going to be the number of iterations we go over the data set. So now we're going to start the training part, the actual, okay, we're going to adjust that final layer thing that we just added, such that it's going to use those features, those weights that were pre-trained. We're going to make this just 1 now, because this will take a decent amount of time. So let's go ahead and create a loop for epic and range epics. Then we're going to keep track of the running loss for every epic, just so we can see how it's doing over time. And then for the data that's in the train loader, so we have the data set, and then we did this train set, which is like the raw data. We pass it to the train loader, and then this is going to batch it all nicely for us. So we're going to get a batch from this train loader. So we want to have this data. We're going to have images coming out of this, and we're also going to have its labels when we unpack this data. And then we're going to also send these images and labels to the GPU. And we should also send the model to the GPU. Now, remember before how we had to go optimizer.0 grad? As Julia said, like PyTorch is keeping track of these gradients under the hood. And then if you just call this loss.backwards that we'll go through, which is like gonna like calculate those gradients, then it'll just keep adding them on top of each other. So we don't want to do that. We want to have our own gradients for every single epic. And then we're going to want to make some predictions, which is going to be your model where we pass in the images. So we're going to get some predictions out of that. And then we're going to have a loss, which is going to be calling our loss function. And then we're going to pass in our predictions and our labels. And it's going to measure, okay, how good is our model doing now based on those predictions. Now we're going to go loss.backward. Is there an S? No. I always do that. Okay. And so now we have those gradient loss.backward that's calculating those gradients, but it hasn't actually done anything to our model. So that's when we do optimizer dot step. And remember how when we declared that we were passing in the model's parameters, and how the only parameters in this model that is now like keeping track of these gradients is just this linear part right here, or this fully connected part rather. So then we're going to have that, but we're also going to update our running loss by adding this loss item. So loss is going to return like a little tensor with like one value in it. So the dot item just has this take out that one item instead of getting that tensor. Now, after every epic, we're going to want to go do something like print. And then f-strings are a nice little Python trick, where if we want to go epic, what epic? Just do some brackets and then type in this epic. We can use variables inside the string. And then we want to say, okay, what was the loss for this epic? Well, it was the running loss that we were just keeping track of. Okay, let's see what this goes. Okay. Prediction about images. No, I have to flip. Yeah, I didn't push the model onto the GPU. I don't think I ran that. Okay. So I'm going to stop that because that's going to take a little while, and we're going to use this handy dandy package, so we're going to see the progress here. Then we're going to wrap this one. TQDM, it's going to essentially add a progress bar. Another good Python tip. And we're going to set the total to this to equal the length of the train loader. And then we should actually divide this by the length of the train loader as well. So we're getting the loss per example. Let's put the per batch. So this parse bar now comes from this TQDM that we just did. So that's a nice little trick to keep track of things when it's going to take a while. Meanwhile, let's create a way. So this is going to train once, but this is on our training data. Let's see how it's actually going to do on data it hasn't seen before. So this is going to be putting this test data and this test loader to use. So we're going to need to keep track of the number of correct. And right now we're going to start that at 0. And then when we're just doing like inference, like we're just doing the forward pass, we don't need to keep track of the gradients at all. You can just call torch.nograd. So what this is doing, it's almost like how you open like a file, but it's like just using torch now with no gradients. And so when we go through all the data that's in the test loader, we still need to kind of do very similar to what we did here. Let's actually copy it up to here. So we're pulling the images and labels from this data, but now the data is coming from the test loader. We still want to push these images and labels onto the GPU where the model is, so it's going to run faster. We don't need to keep track of, we don't need to get rid of any gradients anymore because we're not using any gradients whatsoever with that torch.nograd. We still are making predictions, but now you want to see if the predictions are correct or not. Just yes, no, pretty much. So what we need to do here is get the predicted values that are actually coming out here, and we're going to use torch.max, which works very similar to what Curtis was doing in the numpy.argmax, where it's going to tell us where in that label is like the maximum value, which is what we're interpreting as the network saying that it's that class. So it's going to be something between those 10 classes, and that's going to correspond with like horses or something. So this is going to be coming out of those predictions that we just made. Now for little PyTorch thing, we got a 1 here. So this is going to the documentation some more. Had a comment here. So what it's doing is it's going to take maximum value of each row in the input tensor in the given dimension. So it's just going to like one of these like sub-tensors kind of where it's actually at. It's going to pick out that index where it is, and that's what we're actually going to get. Yeah, we're going to get the value, not the index here. Yeah, it's like the axis that we're going through, like axis through. Yes. So it's like that largest value that it's outputting. It's going to be like, okay, it's this class now. Yes. Exactly. So I just stole this now. So we want to keep track of the total as well. You could maybe say, oh, we just do the length here, but this is going to have batches too. And maybe if like that batch size isn't like a multiple of what's happening there, it might give us a different size. So keeping track of the exact size, we'll keep it exactly what we want. And so the correct here is it's taking this vector that we just got from this max function, and it's going to compare it to the label. So if that indice, yeah, we are getting the indices here. This is the value. So we want the indices, and we're going to correspond to labels, which are those indices of the classes. And then we're going to sum those all up. Because if it equals, that's going to be 1 in Python. And then we're going to get a single value from that, which is going to be our number correct. Anything to clarify there? And then we just go print our accuracy doing transfer learning was, and then again using this nice thing, which is our correct over total times 100. %. Okay, so this is going much slower. You know what it is? Our batch size is really small. So it's worthwhile to stop it, increase this batch size to something like, let's go 512 for now. I always like to keep it like a multiple of 2, because then it's going to fit in memory, right? So it's just runtime, restart and run all. So now it's going to go through everything. If I click that right. It's good. It's doing it, knows where your GPU, it's going to take in our hyperparameters, it's going to load all the data. It's printing that just to see what was in that pre-trained ResNet, loaded our ResNet model onto GPU. Now it's going to start training faster or not. That was too much. It's at 256. So, it's a real world debugging. Data, print that, load the model into GPU, and now start training. Yeah, it's going. That's really good now. Okay. So it's like before, if you imagine on the GPU, there were just like 4 images on that GPU at a time. And so there was like a lot of empty space on that GPU. We weren't utilizing it to its full capacity. But now we just said, okay, fuck it, let's put like 256 at one time on the GPU. And now it's like, it's using like a very good amount of the GPU so that it's going to be able to do, I'll go through the entire data set faster. So this is going to take 4 minutes. So if we go to what happened here, we got a loss after 1 epoch at 0.83. Which is pretty decent. I was comparing it to like if we did like a deeper convolutional neural network, very similar to what Curtis just did before. And if we ran that and trained that for a while, we start that epoch loss at 1.539, which is going to translate to a pretty bad accuracy. And it took how many epochs to get to where we got on just 1 epoch using this pre-train? It took 8 epochs, so that was a solid amount of time to beat that out. So we did in 1 epoch what it took our little like from scratch model 8 epochs to do. So that's kind of like the benefit you get with transfer learning. It already kind of knows what it needs to look for, so it doesn't need to take as much time to train. And we're not like going through like background creating through like all those features, just like that last little end part of that. So you're actually doing less computation that way. So that's where the advantage of transfer learning comes in. And we were able to get accuracy of like 65%, which is actually comparable to if we did from scratch up until like Epoch Gate. I believe this got something like, I did not run that all the way. But the pre-trained model is going to like converge faster. But I do remember that the one we trained from scratch was something around like 60-some%.
Is there a benefit to using transfer learning besides making the process like that? Yeah, you can use less data as well. So say the reason why people use ImageNet as a pre-train is because it sees basically everything, like every single compliment, and then
Massive.
fine-tune it so that if you have a specific set from the say like this data set of 1,000 images of cats, then you can easily transfer. Okay. It seems like convolutional neural networks, even like the terminology we're using, it seems like it really lends itself to image processing. Is it used for anything else?
Yeah, it's actually been using much more in terms of like sequential data. Because if you imagine, so CNNs are biased towards being spatially aware. So like knows what's near like those pixels. Like you could, instead of picking just one pixel, it like looks around at like a group of pixels. So if you imagine that's like words, it's like it looks at like a part of a sentence as opposed to just one word at a time. So it kind of takes into account that sequence. Then there's also some crazy things where people use the idea of like a convolution itself being that it's like Local, like again, it's just one group. Spatially aware, like different direction, and like abstracting that out and applying it onto like graphs and stuff. So yeah, convolutional networks are a very like fundamental part of like machine learning now. Almost there. This took 3 minutes less.
Any other questions?
Yeah, TensorFlow, I don't like it. I don't like it. But 2.0.
Once you're done, then you train it. But in PyTorch, like you can pause it at any moment. You can debug it, for example. And so if you find some bug,
This should be much faster. That was the accuracy one.
well, it should be trained now. Yes.
Yeah, so we're good. We're good. It's gonna take a little. It has to just go through that test loader. Wait, what was it? I had something that's.
I mean, like, personally,
Maybe
I
TensorFlow.
started using TensorFlow as my initially for like a full year, but once I started using PyTorch for like 1 week, I found that it's just way better.
Literally, I knew multiple people that were using TensorFlow, and then they looked at PyTorch and they're like, "Holy shit, this is so much better." It's like TensorFlow is so much more. Mother. What is this?
Yeah, and in terms of Keras, basically, it's PyTorch has all the abstractions. You can do very high level stuff with PyTorch, and you can do very low level stuff.
Well, Keras just kind of keeps you on that top level. I don't know.
Keras is really
It's on top of TensorFlow. It's just like a more abstracted,
just
yeah.
like define layers and then dot it.
Like very similar to in like Curtis's or in Ray, no, where it's like you're doing like the dot convolution.
Yeah.
It's like that. Same thing in Keras. Like this part, it looks very similar in Keras because TensorFlow was trying to copy PyTorch. Did it do it? We got 90%. Okay, we did much better. Good for us. Guess changing that batch size did it, which is interesting. We'll post it on like Piazza, so if you want to play around. Good night. Thank you. See ya. Yeah.
Interview for Eagle.
Yes.
So we are doing exactly.
Oh, what was your name? What was it?
Wait a minute.
Okay, so you're scheduled for tomorrow. Yeah, it's gonna be in the GSU. It's like some of us will like get there early and then we'll like meet you at the stairs or something.
This year is that'll be
Like right as you enter the GSU, coming off of Comac.
right. Okay.
Yeah, so I think we'll watch your emails. So like if you don't see us, like just email.
Okay.
Yeah, so we'll try to send an email tomorrow morning to confirm everything.
Alright.
So look for that. Yeah,
Okay. Thank you.
yeah, sweet. See you then. Got much better accuracy. Nice. Dude, that batch size difference. That made a huge difference.
Yeah.
It's been funny.
Always does.
That's yep. Like I've seen batch size make differences in time, not accuracy, but in this would be very interesting. Stop. Yeah.
It was a not streaming.
No, it was.